do for that. Right. So, no, you don't want that more than once. Right, can everyone hear me? Good, I'm on. Okay, thank you very much for coming to this session. And I'd also like to thank the organisers of GeeCON for this amazing conference and for inviting me. You might have noticed that the introductory slide actually had the name of my co-presenter, who's kind of not here today because he's injured his knee in a skiing accident and he's recovering at the moment. So I'm here as two people, as Maurice Naftalin and as Dmitry Vyazelenko. I've got an introductory slide here, which I kind of will hurry over because it just is like my defense against feeling inadequate. It's these things that I've done and written and places that I've spoken, but I don't really want to go on about them. This is Dmitry, and he's like we're going to miss him today because he's so much more handsome than I am, and actually knows so much more about this stuff. But we developed this together. So yeah, I would just point to this line. He's disorganizer-in-chief of the Unconferences of JCrete and JAlba. You've probably heard of JCrete. You might have heard of JCrete. An unconference is sort of like a conference, only it doesn't have all of the formality of a conference. It's a lot smaller than this, and it's a lot more informal, and you spend a lot more time doing the things that people often value in conferences, which is the corridor chat. So it's small, it's self-organizing, small groups of people just talking about the stuff that really inspires them. So JCrete is in the summer, and I would really strongly recommend people to try to get onto that, but it's very much in demand. JAlba is in Edinburgh. I organize that. I do the local arrangements for that, and it's next week. We still have places if you feel like coming to Edinburgh next week. So that's us. This is the interaction mechanism, the way we ask questions at this conference. It's not. I'm not entirely familiar with it, but we're going to try to make it work. And this is the talk. What lies beneath? So the idea of this talk is that we're going to look at a tiny Java program. So it's not even Hello World. It's smaller than and less complicated than that. And the idea of it the original idea of this talk was that we were going to take a slice all the way down from the Java source code, right through the bytecode and the machine code to the hardware, and see what was involved in executing a very simple program like that. So it turns out this is possibly not a very realistic aim, because even to explain really the most simple program there can be, you've got a lot of work to do. There's really kind of too much to do. But I'm going to cover the bases in the next 3/4 of an hour. I'm afraid it won't go very deep, so for people who know a lot about any of these things, you're going to feel maybe a little disappointed. But we will try to get right to the bottom of what happens. We have a tiny class computer. We're going to see what happens when we type Java computer.java, and we're going to find that even to do the most simple thing, it's really complicated and very interesting. So the stuff that everybody knows to start off with, obviously everybody knows that Java source code gets compiled by JavaC into bytecode, and everybody knows that bytecode is essentially the machine code for the Java virtual machine. And the way that I guess everyone probably knows is that the bytecode is interpreted instruction by instruction and translated into machine code. So the template interpreter has an entry for every bytecode instruction, and there's corresponding machine code. We'll look at just one of those. So here's our program. It consists of 3 methods. There's the method that sort of does the work. It adds 254 to a supplied value. There's a method which computes the value that's going to be supplied, and basically it takes a value that's been supplied to that and it divides it by a constant. We looked for something that was kind of reasonably picturesque. So hex dead beef is a large negative number, and the main method for this calls compute, and it supplies a value as well, and also a large negative number, hex cafe babe. Does anybody know why, does Cafe Babe have any significance for people here? How many people have heard of this before? Okay, quite a lot of people. But does anybody know where it comes from? Sorry? From Gosling, yeah, absolutely. It's kind of politically incorrect now. They used to go to the this is the hex header to every class file. So the bytes that head every class file. And he was looking for inspiration. Well, they went to a coffee bar, and to quote him, the cute baristas there inspired him to choose that particular constant. So the value Cafe Babe gets supplied to the method compute, and that is divided by the dead beef constant. That value is sent to the add method, which adds 254 to it, and the result is going to be 255, because the result of dividing Cafe Babe by dead beef is 1. So you might wonder why we're going to all this trouble to do such a simple thing, and I hope that will become clear. Let's look at the bytecode first of all. So Java C generates the bytecode, and the bytecode, if you can easily be seen, if you run Java P with the verbose flag on the class file, you get something that looks like this. Let's have a closer look at that. There's 3 main components that you see with Java P when you disassemble it. There's a constant pool, which is for all the methods, and it includes things like string constants, for example. It includes literals in the program, and quite a lot of other stuff as well. But we'll just stick with that. And for each method, there's code, obviously, the actual bytecodes themselves, and there's a local variable table. The local variable table doesn't, in fact, get populated until the program's run. So the local variable table contains, essentially, it's a method stack. It's a stack frame. It's the space on the stack frame in this case, for the method compute, and it has on it, when the method is called, the stack frame is initialized with the parameters to the method, and any local variables that are declared, those also go into the local variable table. That's mainly what it's used for. So let's have a look at the execution of this compute method. We need to know that something that doesn't appear in the output of Java P is a data area in the JVM called the operand stack. The JVM is a stack-based machine. It doesn't have registers. It has a stack. There's not really any very clear reason as to why that particular architecture should have been chosen. Stack-based machines were more popular 25 years ago when Java was first being developed, but they weren't that popular then. I mean, register machines generally have been the way that machine architectures have been going, but we have a stack-based machine here. It just makes it a little bit harder to understand what's going on if you're not familiar with it. So the data area, the JVM operand stack is shown at the bottom. The first instruction that's going to be executed is A-load A, A-load 0. A-load means I want to load a reference. Load in this case means I want to put it onto the operand stack, and 0 means I want to get it from the first location in the local variable table. So by convention, when a method is called in the JVM, it's a very strong convention. A reference to the current object, obviously only for an instance method, a reference to the current object is put in the first entry of the local variable table. So virtually all JVM bytecodes, all the bytecodes for every method in Java, always start with A-load 0. And that means that there's a reference to the current object placed on the top of the operand stack. So we go on to I-load 1. I-load 1 means I want to load an integer. That means push an integer onto the operand stack. And in this case, I want to get it from entry number 1, slot 1 of the local variable table. So that, of course, was a supplied value. the first and by the way, the only parameter that was supplied to compute, and it was Cafe Babe. So iLoad1 pushed Cafe Babe onto the top of the operand stack, and naturally the reference to the current object got pushed down one. The next instruction is a load C, which means load a constant, and Java P will tell you where that constant's to come from. In this case, it's from the second element of the constant pool, which is dead beef. So that now gets pushed onto the top of the stack. And now we have on the top of the stack the two elements that we actually want to work with for the first operation of compute. If you look at the top right, the first thing it's going to do is it's going to divide the supplied value, which is now oh, we haven't got that there yet. It wants to divide the supplied value by dead beef. And so the idiv operation, the next one to be performed, does exactly that. It divides the penultimate element on the stack, on the operand stack, by the top one. So we got Cafe Babe divided by dead beef, and then both of those are popped off the stack, and the result is pushed on. So this is characteristic of the way in which the JVM works with the operand stack. This kind of thing happens all the time. The top elements are worked with. So operations like idiv, for example, integer division, doesn't need to supply any operands. It's always going to be using the top elements on the operand stack. Then there's an invoke special. Can't remember why this is invoke special. Maybe it's a private method. Perhaps we declared it as a private method. That would be invoke special. It means that invoke special is used for method invocations which can't be virtual methods. So it would be private and maybe final. Invoke special would be used for that as well. And now that's going to call the add method. And it's going to, and since the add method requires one single integer parameter, that's going to be the top one on the operand stack. That will automatically be done. And then finally, so one is taken off the stack, and it's replaced with the result. It's popped off the stack, and the result of calling the add method is pushed onto the top of the stack. So that's where all that comes from, and that's obviously a very simple piece of bytecode. But that's basically the kind of idea that you're always seeing when you look at the JVM. It is worthwhile becoming familiar. I took a very long time to become familiar with the idea of how the JVM works, but it often can be very useful to have it as a bit of background. Okay, so let's see what happens when this bit of bytecode is executed. If we run Java and we say we supply the print plus print interpreter non-standard flag minus XX plus print interpreter, we get the output of the actual machine code that has been produced, or the assembler that has been produced as a result of this. And it's actually divided into sections because this is the template interpreter, and it doesn't attempt to do anything clever at all. It comes across an idiv instruction. We have an idiv instruction here. That's what it gives you. It gives you all of that. All of that's the machine code for an idiv instruction. So Dimitri and I kind of scratched our heads for quite a while looking at this. x86 assembler's not that easy, not really that easy to understand, especially on modern machines, because it accommodates, the idea of it is to accommodate varying sizes of registers, because the original Intel x86 architecture, it started out as 8 bits. Started out as 4 bits, but I don't think that was, I think they changed the architecture after that. But it accommodates everything from 8 bits up to, well, who knows what width these instructions are going to be. I mean, nowadays, vectorization is giving you like 64-bit parallel instructions. So that makes the machine code pretty hard to understand. But we kind of worked our way through it. There's something at the beginning here which just does nothing more than taking the divisor off the operand stack. Well, it's off the of course, now this thing, idiv actually represents a method in machine code, a function in machine code. So the operands that that the division's being done on, the two things that were taken from the operand stack, now appear on the x86 stack, and they need to be transferred to the to x86 registers, and that's what the code in the blue box does. The next piece of code, so I'm not going to talk about that much more. And at the end, there's a few lines of code which have to do with the template interpreter. It's just standard stuff that allows every block of templated code to work uniformly. But what about this in the middle? So the stuff that's in the blue box in the middle is just what's required in order to do division, integer division on x86. So it looks really complicated. We spent quite a bit of time scratching our heads and trying to work out why was it doing something so complicated when, after all, there is an IDIV instruction on the there's an x86 IDIV instruction. So I don't want to push this, and of course I know not everybody will have seen x86 machine code, but can anybody guess what's going on here? You'll be doing better than we did if you can guess straight away. Yeah?
A higher register is set because division works on two registers.
That's certainly part of it. So one part of the answer is that there's some stuff going on here that division works on two registers, and effectively it produces a result which may overlap more registers than it was using, than it started out using. So in the middle there's an XOR instruction which XORs EDX with itself, and what that's doing is it's zeroing the EDX register, because the result of doing the division between EAX and ECX puts data into the EDX register. So that is a little part of it, yes. But it's not actually the main point as to what's going on there. It's something like that. It's something like that, but it's not an overflow check, because we know that integer overflow isn't checked in Java. And nothing, there's often, people often ask when we do this talk, or talks like this, why does Java never warn you about integer overflow? And the reason for that is because it would be very expensive to do it. At least that's what I believe is the reason for doing it. They never specified that, because machine code doesn't generally, you don't generally get an interrupt raised for integer overflow, and to check for it manually would be very expensive. But it's something like that. No, it's not division by zero, because that would raise an interrupt. So there's actually a problem hidden in the way that Java represents integers. It's not only Java. It's not actually a problem specifically of Java. Not all integers are equal in Java. Right? Do you know a problem, for example, if you're doing math.abs? It doesn't always produce exactly the expected result. It doesn't produce exactly the expected result because there's one value, a positive value, which can't be represented. It's the same magnitude as the corresponding negative value, but it can't be represented as a positive value. No, it's not a prime. The min-int in Java has a magnitude 1 greater than max-int, right? Because of the 2's complement representation of it. So if you try to calculate a number which is as large as min-int, has the same magnitude but is positive, it won't work. So how does that relate to integer division, do you think? What could produce that result, that non-existent integer, by division? Integer min value divided by -1 will produce a result which is not what you want. So what's actually going on in that code there is there's we figured out eventually, is shown in the flowchart. I didn't think I was going to draw many flowcharts again in 2019, but it's quite useful, as it turns out. So the code is checking, is the dividend, the number that's being divided, is it equal to min value? And if it's not, then you're okay, just you can do the division normally. And if it's and if it is, then we're going to check whether the divisor is -1. And if it isn't, then we're in business as well. But if those two conditions occur, then we're going to bypass the division operation. So that's an overhead that you're always getting every time integer division is performed in the template, by the template interpreter. It's really quite a lot of work for a case that's going to arise very, very rarely. So that actually leads us to where we're going with the next thing, which is like this templated code, just it's obviously it can be produced really easily. I mean, it's built into the JVM, and so there's no kind of warm-up time required in order to execute this. But you can see that the overhead of doing this and many other things like this, also all this code at the bottom as well, is going to be very great. And we'll see that there's actually an even bigger loss than that results from it. So to get an idea of the way in which this program could be improved, we can actually improve it by hand. I mean, you can see, I mean, obviously this is kind of a stupid program because the add method is clearly not doing anything very much. You've got the overhead of calling, well, there are many things that are stupid about it, but one stupid thing is that you've got an overhead of calling the add program, which is obviously substantial, when what it's doing is something that could actually be done in the calling program. We know we're meant to keep methods short, and every method should have a specific use and so on. But actually, in terms of efficiency, that's not a particularly good idea. So inlining, actually just manually inlining the code like that, is going to give you better performance. Let's see how much better performance it gives you. We're going to run a benchmark. So of course, we're going to use JMH. We could use other benchmarking harnesses, but JMH is now built into the JDK, so it's the thing to do. And I don't want to talk about the various ways in which JMH has been configured here because there's too much detail. In fact, there's a GitHub repository for everything that's in this talk, which is not on the slides, but which I will tweet afterwards. So we can run that code, and we can also run our improved code. So when we do that inlining, we see we actually get a slight improvement. Instead of running at the score, the lower the score, the better. We've got a slight improvement by modifying the code, but it's obviously not very much. What could be better? Well, what could be better would be to carry that idea of doing that tiny optimization very, very much further, and that, of course, is what the JVM does. Running with only interpreted code like that is not something you would do practically at all, unless what you wanted was to do little experiments like this. So what actually happens is that the JVM runs a profiler, and it observes the code that's being executed. It does that because we don't want optimizations are expensive to do. There's always a trade-off between doing these optimizations. The most expensive the most aggressive optimizations, the ones that will produce the best effect, are very expensive. They'll take quite a long time to do. So you don't want to just do them regardless, because to do that for your entire program would result in you wasting an awful lot of expensive compute time optimizing code that wasn't going to be run very often. So the idea is to profile it, find out what is the most commonly run code, and then to compile that. And so there's a completely separate code is produced. The bytecode is compiled compiled and optimized to assembly, to machine code. So that gives you somewhat better results because you can do things like this. So without inlining, if we say we want to run with -xx without inlining, and now we're talking the inlining here is inlining that the JIT compiler would do. So if we tell the JIT compiler, don't inline, something you would not do in practice ever, I think, not in real life, is you would, the compute method calls the computer benchmark method, that's the framework method, calls computer.compute. Computer.compute does the division here. So it looks quite strange. I had some trouble working this out. One thing that is not completely obvious if you don't look at machine code a lot is because integer division as a machine code instruction is very expensive, much more expensive than most other integer operation, than any other integer operation. There are clever algorithms which will allow you to generate weird numbers like that hex number at the beginning there, that will allow you, provided you're dividing by a constant, it will allow you to avoid doing the division. You can do it with a combination of multiplications and adds, and that's what's going on. That's what's going on there. So the JVM, the JIT compiler, knows that much. And then, of course, the actual add method simply adds. So that's what will happen if you don't inline, if you prevent the compiler from inlining. So the little bit of manual inlining that we did there was nothing compared to what the JIT compiler will do. I mean, inlining, by the way, is a fairly standard compiler optimization. I mean, these compiler optimizations have been, it's a technology that's been developed over 50 years. So you would expect that they would be pretty good by now, but they are pretty good. That's the result with inlining, because everything that we had there can just really be effectively a single instruction. So the performance difference that you get now is really dramatic. So we've gone down from a score of 178 to a score of 3. And that's what happens. So the minus x int in the top two lines there prevents the JIT compiler from working. It says we only want to work with templated code. And the bottom two lines are when we allow the JIT compiler to work. In the first case, we prevent it from inlining, and in the second case, we allow it to inline. Inlining is a very important optimization. So I've heard it called the Uber optimization, the top one, because with inlining, what you can when the compiler is allowed to inline, it gets a larger window of code that it can look at, and so it gets a better picture of what you're doing, and has many more optimizations that it can bring in. And so there are actually, I can't remember the hundreds. I think literally a couple, like more than 100 anyway, more than 100 optimizations that the JVM does. But inlining, I should have made inlining a really big one of those, because it's the one that actually counts for most. It's the one that enables very many of the others. Okay, so now we've got down to optimized code, and the last part of the talk. What I wanted to do was to, we've gone through I haven't talked about source code, but we've gone through bytecode, from source code to bytecode, from bytecode to machine code. Just a very rough, very brief discussion of how we get to machine code. And now what we want to do is we want to look at what happens when we actually get to the actually running on hardware. So Dimitri and I kind of put our heads together and we tried to think, like, what could we have for a box here that would actually be an indication of actual running code? And we couldn't come up with anything better than this. Because this is what quite frequently happens when we actually run our code. So we were lucky because we could find the Pooh Emoji. So sometimes people laugh at that. So now I want to go a little further down and actually look at one very small aspect of execution on hardware. So one of the things I'd like to challenge is the idea that we have. Almost everybody still has this. I mean, I certainly had it until very recently. That a good proxy for a good stand-in for the performance of your code, for how efficient your code is the number of instructions. So you think, well, if I've got more instructions, that's going to be worse because it's going to take the hardware longer to execute them. And if I have fewer instructions, that's going to be better. And so that's actually an idea which is quite firmly implanted in our mind. And if you've done any, if at university you did any work with algorithmic complexity, the big O notation, that will be fairly firmly implanted in your mind. And they told you, well, it's an approximation. And they told you instructions take different lengths of time to execute. But what they didn't tell you was, maybe because it hadn't happened yet, was that machines actually don't really work like that at all anymore. So the architecture on which those sorts of complexity instructions worked has changed a lot. I won't say that it's not interesting to know whether an algorithm has linear complexity or exponential complexity. That's still going to count a lot. But two algorithms with linear complexity may actually behave very, very differently in practice. So the basis on which I learned about computing, well, you can tell, I mean, you can hardly believe that there were computers when I was young, but hey, there were, and this is the kind of block diagram you got for them, and it was really straightforward. So the key thing about this, the key thing about this diagram, is that there's a bus that connects main memory to the CPU, and it's not problematic. So getting data or instructions from main memory, loading them into the CPU, and then executing the instructions on the data you've loaded is not a problem. And now if you look at a modern machine, you see that that's really not the case at all anymore. So if you look at this, you can see that the shared L3 cache on this Ivy Bridge processor, which is now quite old, I think. So in fact, modern machines are show this even more. The shared L3 cache takes up a lot of space on that chip, and within the 4 cores on this chip, there's still more cache. There's level 1 cache and level 2 cache as well. So we're talking about a lot of cache. Where's this cache come from? Why is it so important that on some modern chips it can take up to 80% of the real estate? Well, the answer to that question is that as time has gone by, the speed of processors has increased. Sometimes if you ask people, like, what do they think Moore's law says, they can make the mistake of saying the speed of processors has increased so uniformly over such a long time. They say Moore's law says that processors will double in speed every 18 months. And of course, Moore's law doesn't say anything of the kind. Moore's law says that the density of transistors will double every 18 months. And in fact, for a lot of the history of the microchip, it was true that processors doubled in speed every 18 months. That flattened out quite a long time ago, but they're still really, 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 really fast, and they could be much faster. Meanwhile, memory has got a lot faster, but it's not got faster at anything like the same speed. And the result is that getting the data from main memory to the processor is a really big problem. It's a really big problem because in the time that it takes the data to get from the main memory on a standard memory bus to a modern CPU is somewhere between, it's of the order of 300 or 400, and it can be as much as 1,000 clock cycles. So the processor can be standing idle for a very, very long time, waiting for data if it doesn't know where it's coming from. So this is what modern architectures look like. They have the memory is at the bottom of a hierarchy. This memory hierarchy, by the way, has existed ever since there's been computers, but it's become a lot more acute. The problems have become a lot more acute and actually migrated onto the chip in the last 10 years. So at the bottom you've got this, what used to be tapes or disks or flash drives or something really slow, but now memory is something that's really slow. And you've got a series of caches which are designed to be filled up progressively. As you go up this hierarchy, they get smaller and faster and more power hungry and more expensive. And at the top, the level 1 caches, which are right next to the processor, are so fast that the processor can actually they're still significantly slower than the processor, but the retrieval time isn't a huge problem. So typically, there's a factor of about 4 in performance, in speed of retrieval, as you go down this hierarchy. So level 1 cache takes about 4 times as long to retrieve data as the processor can use it. The level 2 cache takes about 4 times as long as the level 1 cache, and so on, and so on. So the idea of these caches is to create a kind of pipeline which is kept filled with data and with instructions so that the processor can always be fed and can be kept hot. Otherwise the processor is going to be standing there tapping its foot, waiting for data to come from main memory, data and instructions to come from main memory for the vast majority of its time. So modern hardware is very, very highly tuned to trying to work out how to get the right things into the cache. A cache miss is incredibly expensive. And in fact, if you have many cache misses in your program, that performance hit will dominate the execution of your program. So in fact, the number of instructions don't matter at all. You could have a program that was really economical in terms of the number of instructions it executed. But if each one required you to refresh the cache right from the bottom, it would perform really horribly. So what's this got to do with Java? Well, the answer is, well, let's take one step further. Let's look at one of the strategies that hardware uses for the modern hardware uses in order to try to predict what data is going to be required to put into that cache pipeline. This is called stride prefetching. The diagram just shows main memory at the bottom, the level one cache just roughly shown next to the processor, and entries in the level one cache corresponding to different locations in the main memory. So the idea of stride prefetching is that the processor watches where the data is being retrieved from in the main memory, and if it's something reasonably regular, like this, supposing, for example, you're stepping down an array of int, then the processor can figure out, the hardware can figure out, hey, I've got a very good idea what value is going to be required next, because I can see it's taking, say, every second value from the array, and it can start preloading the cache. And so stride prefetching is this really great and very, very effective mechanism for making sure that you don't get a lot of cache misses and cache refreshes. So how does this relate to Java programs? Well, the answer is, of course, that Java, which is an object-oriented language and therefore depends heavily on references, can allocate data in virtually any part of main memory. So typically, these things called data-dependent loads are following pointers or following references in your objects, which are all over the place. So that particular optimization, only one of many, but a very important one, is completely frustrated by an object-oriented program. So this is just a basic problem about dealing with objects in a dynamic heap that like Java has. And this is a major reason as to why there's such interest in value objects, which are part of the Project Valhalla that is in the labs at Oracle. The idea of that is to try, without giving up all of the semantic benefits of working with objects, because we know that object-oriented programming has many advantages over working with primitives, but to try to organize them in the same way as primitives are organized, because you're going to get a huge performance improvement. By the way, I think I mentioned that just to show how wrong it's possible to be, I mentioned I showed in the introductory slides in the book that we wrote the book I wrote with Phil Wadler in 2006. We looked at collections and we looked at arrays of primitives, and we said, these arrays of primitives, they're useless. They've got no functionality. Arrays, we said, should be considered a legacy data type in Java. And that was 13 years ago. So, I get a lot of things wrong, and that was just another one. So arrays still have not actually, we're not out of the woods with them yet. So the next slides, which I'm going to skip over because I'm a little short of time, the next slides actually show how much worse this problem is than even I've been saying, because the data in main memory is organized into pages because the processor works with virtual addresses, not with physical ones. So there has to be a translation mechanism between them. So I'll just briefly cover this. A translation mechanism is something called a translation buffer. Also sometimes you see it called a TLB. It's a translation look-aside buffer. I'm not quite sure what that means. And it translates a virtual address into an actual physical address along the bottom. But this translation buffer itself obviously has to be retrieved from memory, and it's only got a limited size. So there's another possible cache miss involved there. So it can be that actually for any one of these data-dependent loads, you first of all, you get a virtual address, but you've first of all got to load the appropriate entry into the translation buffer, which means coming up a series of caches. And only then can you find the physical address from which it's got to be loaded into the level 1 cache, which means another set of retrievals. So you can see that this is actually a really serious problem. These things, all these retrievals have an overhead which completely dwarfs the execution time of the actual instructions you're working with. So let me skip over that and look at how we could measure cache friendliness. I don't think I've got a slide about actually forward. 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 Come on. Right. Good. So you can in fact measure cache friendliness using JMH again. JMH is this great tool. It'll actually allow you to hook up the things like perfasm, which is the Unix tool that will actually allow you to look at the hardware counters. So we can get very full information about what's going on. And of course, I obviously want to say that these tools are all open source and free. I mean, you can buy expensive environments from at enterprise level for doing the same kind of thing, and they may be slightly more usable. But actually, JMH and perfasm is a great combination. So here I've got a little program that's designed to compare the performance of a linked list, kind of a widely reviled, disliked collection, member of the collection framework, and a primitive array. And they're doing the same thing. We're basically just iterating over them, and we're actually throwing the data away that we retrieved. So it's just really how quickly can we actually get at the data in these two structures. And for linked list, this is what it looks like. With a list of length, the list is I ran it with four different versions, a list varying from 1K in length to 511K. And the performance drops dramatically. So you see the performance, the number of nanoseconds per operation increases by a factor of 4 as you go up to as the list increases in size. And when we look a little further into it, we see what's going on. We see that the clock ticks per instruction is going up in the same kind of way. So the instructions themselves are much slower. So, and as you would expect, the number of cycles that each operation requires goes up, but the number of instructions is constant. Of course, the number of instructions is constant for each operation because they're doing the same thing. It's just stepping down a linked list. So all of that difference, all of that huge difference, a factor of 4 here, is caused by level 1 cache misses. Well, by cache misses. And you see, it's not actually a very big increase. If you can see, this is what perfasm tells us. We're only talking about 1 cache miss per operation. It doesn't sound like an awful lot, but when you think of how slow those cache misses are, how long they take, you can see that that's actually really going to make a very big difference to the performance. So that's the cache. This is the level 1 cache, and you can also see the last level cache as well, which is the level 3 cache, is also getting significantly worse as well. But the real secret there lies in these misses, and once you see them going up like that, you know how serious, you've got a serious problem. So if we compare that with the primitive array. Well, of course, the number of instructions is naturally the same here as well. And it's a little bit less because, of course, stepping down a primitive array doesn't involve following a pointer. So all you need to do is just increment the instruction count. Increment the address by 1. So it's going to be a little bit quicker. I think it's about half as many instructions. But the difference is, though, that the performance stays the same. we're really not bothered about the increasing size, and you can see that the cache misses are only beginning to very, very, very little to creep up at the very largest size of the of array. So that's just a kind of dramatic demonstration of how important cache misses are to the actual performance of a program. And in the context of a talk that's supposed to go right down to the hardware, it's only a tiny slice of things you should be interested in the hardware. But I thought it was quite an interesting one. And it does tell us something as Java programmers about what to worry about if we are worrying about performance. I mean, you shouldn't be worrying about performance nearly all the time, of course. People worry far too much about performance. But if you are worried about it, well, one thing not to do is to use linked list. Nobody loves linked list, not even the guy who created it, Josh Bloch. It's kind of sad. I mean, it's a plausible enough looking data structure, but it's really not very good. Okay, so conclusions. Well, I don't really have very many conclusions. The biggest conclusion that I have to this talk is you should be interested in this stuff. It's so easy as a Java programmer and so tempting to just think, to look at the source code and to just go no further. But actually, if we really want to understand what's going on with our work, we should understand it in a much fuller way. I don't expect. I mean, I don't claim that I understand the hardware particularly well. I don't. I mean, but I have read a book about it, so that puts me ahead of some Java programmers at least. And I do think, if we want to take our work seriously, we should have a feel for what's going on all the way down. Otherwise, we're really thinking that Java works by magic, and I'm not very keen about that. Sufficiently advanced technology. This is a very famous quote in UK culture, anyway, about technology. So Arthur C. Clarke, well-known science fiction writer, is supposed to have said, "Any sufficiently advanced technology is indistinguishable from magic," and that's actually how a lot of people perceive the world now. Well, I don't think we should be perceiving our world in that way. And I think so. Understanding this stuff isn't as hard as you think. It looks very mysterious, but actually there's a lot of really good tools. So looking at the blog like Mechanical Sympathy, looking at JMH, using JMH, definitely looking at JitWatch, the third one of those, which I should really highly recommend. It was produced by Chris Newland, who wanted to understand how these things worked, and for himself built this amazing tool, which is really excellent, and tells you a huge amount about what's happening. And again, for very little cost, no cost in money, and not much cost actually in the investment of your time. So be curious about this stuff. It's really worth it. Thank you very much. How do we look?
One question and one comment.
Okay. So I've got a question. The call to add probably clears two slots, the int and this. At the end, there's only the int. Oh, it's gone away. Here it is. At the end, there is only the int on the stack when iReturn is reached. The call to add probably clears two slots, int and this. Okay, I didn't think that was the case, but I'll take that as a very likely valid comment. And Heinz is asking, in the linked list example, were the nodes shuffled over time? No, they were not. They were not shuffled over time. This is it was just the list was left alone. I did ensure for the linked list that they were. Oh, sorry, you'd like your phone back. I did ensure that the data was properly disorganized. In other words, pointing all over the place. But no, they weren't changed once the program started execution. Right. Any more? We've got 25 seconds left. What was the tool used with JMH to measure character? That was JMH with perfasm. Yeah, so you can hook that up. So if you want to do that, the bottom reference here, building HSDIS is something, the extra you have to add to the JDK in order to produce, because otherwise the assembler doesn't come out as assembler, it just comes out as machine code. So HSDIS is this thing which will translate those, will give you the interpretation of those things as assembler mnemonics. And with that and perfasm, you can see what we got from the you can see what we got from the output. And not another one. Oh, we're down to 0. I can't answer it. What do you think? Should I just say to come and see me?
What do you prefer? So
How long a break
have
have we?
2 votes, so maybe we can answer from this one.
But I've answered that one. That's the one I've already answered. Yeah.
This one is already done. This one is already done.
What is the way to improve L1 cache hits in this particular case of linked list example? Well, the one thing that you could do. So that is an interesting question, because like this looks pretty desperate. So one thing that I have thought of doing is, if you've got a data structure which you're going to build and then repeatedly iterate over, as we did here, it might well be worthwhile organizing it in a way that is not going to, I mean, in this case, the way that I created it was to ensure that the objects were scattered around in memory in a fairly random way. Now I have actually thought that you might be able to improve your data locality by expensively, on a one-off basis, actually effectively compacting the data. And there may be use cases where that is worth doing. Quite honestly, I think that this particular question says, what about linked list? And I don't think actually linked list is I just don't think it's a great data structure if you're really concerned with performance. It uses a huge amount of space because it's doubly linked. And the more space you use, the more likely you are to get a problem with this kind of thing, and of course with garbage collection. So I think the answer is basically that Josh is right about this thing, this monster that he created. So that's my answer about L1 cache hits.
Okay, so maybe we have time for one more.
One more. I've got time for one more.
And this one have 1 vote, so maybe.
It's got 1 vote. The operations in bytecode were numbered 0, 1, 2, 4, 5, 8 or something. No, so the bytecode numbering was not that wasn't the numbering of the operations. That was numbering their location in the JVM's instruction cache. So they were those looked like they were irregular because the instructions had different lengths. So that's why there's 1 byte instruction and there's 2 byte instructions and so on, and that's why the numbering looked a bit odd. Okay, so that's all we have time for. Obviously, I'm around now if you want to chat about this. Thank you very much for your attention.